with everyone, then I'll come also over here. Hello, and I'd then like to start the session. Yeah, on the domain ontology harmonization for material science. So the first presentation is by Joanna Morgado and Dirk Hell. It will be given by Joanna Morgado, who's from the Fraunhofer EVM, the Institute for Materials. How do you call it in English?
Mechanics of Materials.
Mechanics of Materials. Werkstoff in Freiburg, and she's also they're also a partner in the OntoCommons project and also a number of other projects, in particular in the characterization area. We're working together there as well, and she will give a presentation on that work and on the domain harmonization. We still have to, we have to sort out the projector here. We have some physical media to deal with. That's coming up. Yes.
Okay, so now I have to share. Share screen. Okay. And now, how do I do it? Yeah. Playing the video, but I don't see the presentation. I see the screen. Maybe it isn't. I did. Try again.
You have to click the button at the bottom. Partager l'audio.
This?
Yes. Oh, and oh no, not you don't. Yeah, exactly. That. And then you have to click. Yes.
Okay, and now if I go like this.
Okay. Yeah. Mm-hmm.
So can you hear?
This one.
Oh, yeah. Okay. Yes. Yes. Yeah. Otherwise, yeah.
Okay. Can you also hear me? Someone from the that is attending remotely. Can you say that you are able to hear us and see the presentation in full screen? Hello?
I can hear you.
Yes, and also the presentation? Can you see also, Pedro?
Mm-hmm. Yes, yes.
Okay, then I will start. Okay, so first of all, welcome to the presentation and thank you for your time. The talk is entitled Towards Semantic-Driven Digitalization in Material Science and Engineering, Interoperability, Ontologies, and Data Spaces. And this presentation has been done in collaboration with my colleagues that are mentioned as authors. And even though the title is quite generic, I will show some examples and that we develop in our team, and I will try when I'm doing these examples to address some topics that are concerning with the topic of this session, which is harmonization of domain ontologies. Here is the outline of my presentation. So I'll start with the motivation. Then I will demonstrate some of these cases that we have been working on for the different projects, and therefore I will speak about the ontologies that we have been developing in the domain of material science. And afterwards, I will also speak about the data space and the marketplaces, which are concepts that we are also been working on in our team. So the development of new materials is traditionally very expensive. It's time consuming and requires a lot of trial and errors, and is also inefficient. When we need to develop a new material, we need to take into consideration a lot of aspects, and this figure here on the left of this slide that shows some of the aspects and stages that we need to conduct while developing a new product. And there are many steps and many aspects to take into account. There are a lot of data being generated during all these stages. And if we want to also ensure that our material needs to be sustainable by design, we also need to take into consideration the overall life cycle from the extraction of the raw material up to its disposal, its reuse, or also recycling. So you can see that there are a lot of aspects and a lot of data that we need to take into consideration in order to be able to take well-informed decisions about our new materials. A big problem with this, or with the workflows that we still follow with respect to materials development, is that these workflows are or rely in a data infrastructure that is characterized by many silos. So data is not seamlessly exchanged across the different materials development steps, and it creates a big problem because it means that we cannot integrate all the data, we cannot make use of all the data that we have available, and therefore we cannot draw our decisions upon it. And here are just listed some of the issues that are part of that concern this new materials development process. So most of the data is provided under various schemas and formats that are incompatible with each other. The information is therefore difficult, the information transfer. We have disparate and isolated data resources that we cannot all access, and essentially we are wasting a lot of resource and many time and efforts every time we need to develop a new material. And there should be a way to make this process more, or to accelerate this process and make it more efficient. So ontologies can facilitate this interoperability of data, and this figure just tries to illustrate what it can do. So essentially, ontologies can enable us to capture in an explicit and shared manner all the adequate metadata and data meaning, and this enables that we have, in the end, data models that provide a common language that each tool that we work with and that we need to use within our product development can understand, and therefore this can facilitate interoperability of the data, can facilitate uniform structure of our data, and it can also enable to create data sets that are compatible and that in the end are harmonized and can be combined. Now I will show some use cases, some examples of the work that we did in our team concerning ontology development. And now in each of these use cases, I will also raise some questions about the harmonization and what we did in this direction. So I'll start with the project, which is called Urwerk. And in this project, essentially, we wanted to study the benefits of structured data, materials data, facilitated by knowledge graph and ontologies, and also to understand how it could be used in order to identify new relationships or new correlations between the data. So the ontologies, again, in this project were used to provide a shared vocabulary that enables us to describe the tests that we are interested in. So in this case, we were working, or we wanted to describe the ontology fatigue tests. And also we wanted to be able to capture in our ontologies the process history, for instance, of a type of still, including the descriptions about methodology, the hardening and factoring processes. And all the ontologies that we developed in this project also needed to be able to answer some specific competency questions. And here in this slide, I just list some of them. And what we did in this project, so we started with the data that is generated from a tensile test, and this data is essentially captured or provided in an Excel sheet. And this we actually have in our institute quite large database provided in an Excel sheet that contains 110 materials, 1,100 testing series, and 22,000 experiments. So the first step was to try to convert this Excel into RDF and to map this data to align this data with our ontologies. And for that, we have to first have an ontology, and in this project, we develop an ontology that is able to capture the properties of the specimens that we analyze, the manufacturing processes, the different types of stills, categories of stills that we are interested in, the series. And this ontology is already available in GitHub and is publicly available in GitHub. And essentially, in terms of harmonization, what we had to do in this project was to align specific domain concepts that are of relevance for our use case with a top-level ontology, which is the MO. So we had to do this harmonization exercise in this project. In addition, it means that we had to, what we did was essentially to try to place the concepts that are relevant for our use case into the right place, under the right class in EMO, and also the relationships under the right parent relationship in EMO. In addition to that, we also had the need to represent different classes of stills, and there are a lot of standards that already describe different categories of stills. So one of the questions that we had during this project was how can we align this ontology with existing standards? So for the purpose of this project, what we essentially did was to use some of the headers of the standards or the categories that we needed for these projects, and we placed or created classes with these labels, and we place them within our ontology. But is this actually the right way to do it? This is a question that I add here, and I believe we can also discuss it later afterwards. And this slide here, I just wanted to try to show you the ontologies in action. So how do we actually use the ontology in the end? So as I mentioned in the very beginning, in this project, we wanted to be able to capture information about the process, the characterization experiment, and also information about the material, the properties of the material. In the end, we created a lot of triples from the Excel database. And what we see here in the graph is just a screenshot of a Jupyter notebook. And it is very user-friendly, so essentially it's provided with some widgets, and these drop-down widgets, with these drop-down widgets, you can just choose the process that you want to evaluate. So here you have a process for a variant of still, and behind this widget we have a query to the database that provides us, or that essentially returns to us information about the heat treatment in the manufacturing process of this steel. And here you can see plotted the data that we have about these heat treatments. So you can see that we have 4 types of heat treatments in this process, the duration, and you can see that we have different types of tempering, and this is due to the environments conditions. Here I don't show it, but in the ontology we also describe the conditions of these processes. Now I will speak about another use case, which we are working on in the React project. So in this project, we want to develop multi-scale simulation workflows, and we want to improve the fair characteristics of these workflows. So essentially, we are developing, or we have simulations that conduct calculations at the various scales, and we want to ensure interoperability across these different scales. And to do that, we try to develop ontologies that can be used to capture the workflow, so the different steps, the different calculations, the specifications of each calculation. And here on the right-hand side of this slide, I just show you a portion of some of the more generic concepts of the ontology that we use in order to describe our workflows. And in this project, we use again EMO, and we also have to define concepts, for instance, for workflow, simulation, and calculation. These are quite generic, and at the time, we define these concepts based on the MODA and the CWA, and this is based on the previous EMO version. So now I know that things are changing. Potentially, we need to adapt this model to the new version. But I just want to show you that this is some work that we did, and again, this is one representation of workflows, but there are many of us that are doing the same type of calculations, and I believe that it will be useful to have some kind of harmonized model for representing workflows and to that we all can use in order to annotate our computations or our simulations. Since we use CWL, so the Common Workflow Language, as the runner, the actual executor of our workflow, and use these standards as well, we need to align the model that we develop that captures not only the workflow and the sequence of steps, but also the specification of the simulations with the standard that describes the engine that is used in order to describe every step that we run, but via the engine that we use. Because then every workflow runner, we have this specific schema, and we need to be able to align the schema from the workflow runner with the schema that we develop for the description of workflows. The ontology that we developed follows a modular design. It means that this ontology contains several models, contains a generic one with concepts like this one, which are very generic, and then contains more specific models that contain concepts about electronic, atomistic, mesoscopic, and continuous simulations. Just to give you an idea, these are some of the concepts that we have added to our ontology. Concepts that are able to describe the simulation settings, reaction mechanisms, and the energetics. Another use case that I want to show you is a use case from a project called Stream. And in this project, actually, we had to do some more valuable activities, I'll say, in the domain of harmonization. So essentially, in this project, what we are developing is the LDM, so the Leibniz Data Manager. And this component here is able to extract data from different databases, and the data that is provided in these different databases is described using different ontologies and different models. So, and a user can then observe the data also via a graphical user interface. So this is also a component of this project. But how can we query data seamlessly from different data sources based on different schemas? So what we do in this project is represented in this slide. So essentially, we have the LDM system is based on a schema that we call the MATWORK ontology that contains metadata or relevant metadata representation that can be used to describe any type of, in a generic manner, every data set that we have stored or that we are interested in this project. So essentially, what we do is a user connects with the stream infrastructure. Then he writes something of this sort. So he wants to know the tensile strength for a certain material. Then we trigger a StarQL query that is actually executed using the Matlock language. And in order to be able to actually get the data that is represented with different ontologies, we need to align the Matlock ontology with the concepts from each of the other ontologies. And this is a work that we are doing. So we are aligning this Matlock ontology that acts as a glue with the other, in this case, MO-based ontologies. So as I represent here in this slide, the Matlock ontology represents more generic classes such as study, experiment, simulation, run, protocol and method, observer and study. And the MO-based ontologies and nomad ontologies represent we have concepts that are more specific to their domain. So for instance, the ontologies that we are developing describe tensile tests and the stress relaxation tests. And we use some of these strategies in order to do the alignment between Matlock and MO concepts. So for instance, for some cases, it is, it makes sense to say that a class in MO is equivalent to another class in Matlock, but for other cases, this is not suitable. So we use COS, and essentially these are just some strategies that we are currently implementing. So this is ongoing work, and we hope we can get in the future that we can present actually how it works, how this alignment works, and how valuable also it is. Okay, so now I will just briefly present the concept of data spaces that we are also developing in our team. So for us, a data space, when we speak about data space, we think about ontologies with databases or with databases. And we are creating a concept in our team, which is the DSMS, Data Space Management System. And this is represented here in this figure. And essentially, we have a data space that combines several databases, and so it means that where you can store different types of data. And this data space uses ontology in order to provide a schema that we can use to annotate the data and facilitate the harmonization of this data. So essentially, the data space enables the handling of heterogeneous data sets, and which enables in the end the production of compatible and comparable data sets that can be very valuable for to drive AI and machine learning. So in this project, we can see how the overall framework that we are developing, and that uses the DSMS concept. So essentially, we have data from tensile tests, from a tensile test characterization process. Then what we do first is we need to be able to integrate this data with data models. So we need to annotate this data using ontologies that we are developing that capture all the relevant concepts. Once we have the data integrated with the models that we are developing, we then store all this data and metadata in the DSMS. And the advantage of using such kind of framework is that all the data that we essentially done in the DSMS is annotated and is harmonized, and therefore can be seamlessly shared with other sources, between other sources. The last concept that I will speak about is the marketplace. So essentially, the marketplace is one stop shop technology for materials modeling and simulation. It is a web-based application, and this web-based application enables or comprise different services. For instance, we are able to create and explore, so create data and explore the different materials, explore different software, we are able to interact and get some advice. So we have some translation services, education, training, and we also are able to use the marketplace to find the right software, the right tool that we can use to run a simulation that we are interested in. We are also able to build our own simulation workflow within the marketplace, and in the marketplace, since we also use ontologies in order to annotate our data, we also are able to to essentially facilitate the integration between the data and the different simulation solutions that we have available. So this slide here just provides some highlights the main concepts behind the marketplace technology. So one of the main concepts is interoperability. So the marketplace enables the seamless communication between the different services and tools that it provides. In order to do so, it is based on use ontologies that can be used to provide the shared and common schema to represent the data and the services that are provided in the marketplace. The user needs it can be just in the marketplace. It can have different roles. The users of the marketplace can also register apps that others can access and use. And essentially, the platform, our platform, enables essentially provide infrastructure that users can use in order to adapt it or to build their own workflows and solve their materials modeling problems. So here I just show in this slide a screenshot of the web application of the marketplace. Oh, it looks like, and essentially we have on the left side three widgets. We can create, explore, and then go to the App Store. So I give you an example. If you go to create, you can see this page here that contains the possibility to create a software, organization, or expert. So if you click on software, you can add your software, and you can also describe your software. And you have here some categories, and all these categories here are defined in an ontology. Then you can do the same with experts. You can click in the experts widget. Then you have your name, your institution, and you can also describe further what are the main competencies, the materials that you work with, and all this information then can be used to look for the right expert. So essentially, we have a search engine which is able which uses the ontologies that we developed. And here is an example of a search for silica-based material and soldering. So these are the softwares that enable simulation on this type of materials, and the experts that are experts on this material and on this type of process. So to conclude, the material science challenge are actually to be able to improve and accelerate the materials process and product design, and in a holistic manner, and using more sustainable solutions. So we need really to try to develop more sustainable materials, and also to try to get more knowledge about the process, structure, and property and performance chain, as it is represented here in this image, which is the key element for the material science, and in order to facilitate also the development of new materials. And if you have this type of knowledge, so this type of relationships stored in the database, we can use this information to actually screen for a material which satisfies a certain combination of properties. The solution to solve this challenge, as I mentioned as well, would be to combine the typical integrated computational materials engineering with artificial intelligence. So you can see here in this triangle. So we have the classical modeling and simulation, and we can essentially use semantic technologies to facilitate the exchange of data and the combination of data between modeling and simulation. Then this data can be stored in a useful manner into data spaces or marketplaces, and this is useful or can be used in order to feed AI and machine learning frameworks that can support us in making more well-informed decisions about the materials and also processes. And that's all.
Thank you. Thanks so much. Thank you, Anna, for really great overview of many different projects. Maybe we can also see back the online system here. So please also add your questions online in the chat. We will also look at that. Are there any questions here from the audience?
So thank you. Very interesting for different areas where you're very challenging. One of the earlier slides you spoke about how you look at data coming from process and how you use ontology to map that data through. The question is, do you have to look at those parameters separately and then add the data structure to it? Or how did you get along with the data independent?
So essentially, I mentioned it for one of the projects in the Utrecht project. Maybe I can show the slide quickly. Where is this? Yeah, in this slide. So essentially, we actually started with the data, not with the model for this particular use case. And the data provide us the information about what were the requirements for our model, what we actually need to represent, which information we want to have captured in our ontology. Could have been the other way around, but in this case, we started from the data. Yes, exactly. And usually this is also very beneficial because when you develop on ontology, right, you develop a model that then we need to instantiate, and the instance are what will it's what we can connect with the actual data that we have. And sometimes when you do the instantiation of the model or you create your A box, you can have some inconsistencies when you don't take into consideration the data from the very beginning. So taking the data into consideration from the beginning ensures also that the model is consistent with the data and that you want to try to represent, and the problem that you want actually to capture. So this was an important conclusion actually from this project.
So that's good, because the other question I had was quite related to the same thing as well. Each one has got disparate data, because you touched on disparate data as well. That's a very good premise, the problem you spoke about. How do you go along when you have disparate data? Because each of the data sets, I'm not even talking about the quality at this stage.
Okay.
How would you then, because this is easy, okay?
This is one. Okay, I think this is more complex because here we have different different formats, different representation of data. So essentially, we have to create a generic model that acts as a glue, and we have to align the models that represent each of these data sets, or only some concepts, not all the concepts, only the ones that we capture in this ontology. And essentially that's what we did. We have one model that facilitates the query of information that is presented in this data files. Yes.
So I assume each of those data files have already been processed, and it's just leaving an output waiting to be collected. Does that make sense? Take your fatigue test again.
Yes.
Loop.
So so here we have the data plus the metadata. We have both data plus metadata. And essentially we use the metadata representation to do the queries. Yeah.
The advantage of that on a classical database, this is the richness of the questions. What is your
Okay, yeah. What's the advantage relative to a classical database system here?
The graph database. You mean?
I think he means regular database. So traditionally, what you would do is you'd have these disparate data with specific data structures which you program in syntax, and probably we create an open source platform for maybe a Python language, just capture data and then present it in format the user will see.
Yeah, exactly. And usually in the conventional database, right, usually have the IT team that deals with the schemas, and sometimes a normal user doesn't know how these schemas are made. You need to ask the IT to provide you this information. Here we actually have a model that really captures the knowledge, that it uses the concepts that you know, and it can also be very easy for domain experts to find information.
Okay, so the fact that the domain expert knows the ontology allow him to imagine what he can get.
Yeah, exactly. Okay. And not only there are other benefits that are inherent to to all the database work, of course. When you need to add a new concept or a new column in the table in the database, the graph databases offers more flexibility in this aspect. So there are several benefits.
I have a question. If you go down to the few slides, so down to this matchbook, I think that shows it. Yeah, what the nature of this is. So what you're saying is that this is the nature of it is to say that if I have a table where I have a certain quantity with a certain name, so is this basically connecting the metadata? So I have and then have another data set with where this is named slightly differently. Is that what this system does? Or because if what I don't understand is if this is another ontology, why don't you just use MO here? Why do you need to create another ontology?
So this was a requirement from the project. So essentially use MO and other top-level ontologies to describe different data sets. And then we want to have a common language that...
But that is the ontology, is the common language.
Yes.
Why do you need another common language?
I mean, yes, this is the common language, but you mentioned that we have another data set that is represented with another schema, not with this ontology. And use a single query to access that knowledge.
Yes. Yeah. So this represents the link. That's what I mean. So this is not, in that sense, it's what we call like a data model ontology. Does that provide the link to the specific representation in the database, or is it? Yeah, it must.
Could I? Are you saying that is an application level structure?
Yeah, basically that's yeah.
Rather than a direct top level, because I think you're coming from the top level perspective. But I think what she's done is what I relate to as well, because when I tend to do my data, I've done this umpteen times, because I know as a data what I need, I understand the structure. And I would like that model to represent, or the output to represent, because I don't want to go through all of the APIs, which only a software library built in to do it, so it's easier. I think what you're asking is, why haven't you used the top level library? she
I mean,
has
the one thing is the concept. So the concept should be agreed
Mhm.
in like MO or whatever. I don't need yet another ontology for that, right? But then this concept is implemented in many different ways in different databases. So I need to map what that concept means for this database, for that database, for that database, and that's where this middle layer comes.
Perhaps the question there is, did you, when you created the ontology, did you use the metrics used by ML?
So this ontology, maybe I could
The next slide where you talk about.
So this one is not based on ML, the network ontology.
No.
Essentially, it captures only some more high-level metadata. So, what is if the data set represents an experiment, if it represents a computation, what was the user? So, it's essentially a more compact schema. I would say simpler schema that represents the data, and we have and it's a common language to access the data that is. For this application,
Okay.
I mean, it's specific to this application, but we could use any ontology. But this system runs or enables the queries for using this application or this ontology. It's like for instance, when you have the ontology portal, right? You also have a schema that describes
exactly.
the ontology, the author, and you can do searches based on this schema. And here is the same. You can do searches based on this schema, and you could do even a second query that already incorporates more specific information, and this more specific query will contain terms from ML. But is in case you want to know more about the experiment. Here you are still at a very high-level description. You don't have all the details. I don't know if.
I've just been reading it. It's quite. I mean, I never heard of it. So thank you for introducing it. I think it's actually quite a neat and tidy ontology, but it probably overlaps very substantially with MO. It contains a lot of useful stuff. Like, what is the activity? Is it a test? What standard was the test run?
Exactly, that's my question. Why do you not think?
So well, it's just we live in the real world. It's there, and
the project as well. The projects have also a specification, and within this project, this was also a requirement.
So what you said, I think, is it's the application perspective, and you somehow have to marry that with the others.
So the way I have done this, the same thing is, I go and search what's there and what works with me. I just pick that.
Yeah. So I'm just picking up. So I don't want to pick on it, but it seems to be the topic of very much to the topic of this session, right? So how do we practically also achieve this harmonization? This is what you're doing.
I don't know if I have some colleagues because
I'm trying to understand.
I have to be honest. So this part of the development is also the concern of other colleagues of mine. I don't know if someone is here that potentially could answer better.
The other thing I would see it as is that I am still at that application level because I'm the end user. I'm not looking at that level yet. Somebody asked me earlier, have you stopped thinking about it? I'm miles away. I'm still here. We have a level to get things done. Probably take more experience and expertise to get to that level.
So maybe we can pick it up again. I don't want to keep Pedro from giving his talk, but thank you very much. We'll have some more opportunity then also in the panel discussion. So I will. Okay.
Okay.
Yes. So. Hello. So
yes.
So our next speaker is Professor Pedro Patella. He used to work for many years, or maybe still does. You have to correct me, at the BAM, at the German Materials Institute, and is involved with many projects. And you better introduce all of the things that you are doing from your side.
Fine.
Don't make a mistake. And I would like to
I'll come back to that soon, but I'm just trying to find my PowerPoint presentation here on the screen, and I didn't find it. Okay. Do you get it now?
Yeah, we are getting there.
Okay.
Now,
Is that my first slide?
we see the first slide. I think everything looks
Fine.
great. You could hide this. Yeah, the Ausblenden. That's just like.
Yes, that's okay. Is that
yeah.
okay now?
Yeah, first, and
Great.
everything fine. Over to you.
Yes, thank you, Garrett, and thank you very much for the invitation to present. I'll give you an overview of our platform, Material Digital. It's a huge project. It's funding by BMBF, by our Ministry of Research in Germany. And I am currently with IMM in Freiburg as Joanna. But as Gerhard mentioned, I was for 30 years here in Berlin with BAM, that's our Federal Institute for Materials Research and Testing, similar to NIST in the US. And we are working since about 3 years with this large project on digitalization or digital representation of materials. The idea is to give the added values that they're looking for, both from the materials side aspect, where you go over a huge aspect or many length scales and many different aspects of the materials, and also for the materials engineering, where you go from rolling to the heat treating and so until complete parts of any machine, and how to improve that. Those are two aspects that are important, and also very important is the digital representation is a key issue in implementing the circular economy. All the aspects that we have to do with recycling, considering the whole life cycle of a component. Ministry implemented this initiative, and that's the idea to take the data or the knowledge from the scientific community or generated by industrial companies, and to provide a platform which can supply those information to the whole society. That's the basic idea. And in order to do that, in the first phase, or phase 0, they funded this platform Material Digital, where I'm working at. And in 2 second phases, the phase 1 are 13 products. I will describe them in short. And they started last year. And in the beginning of next year, they will start a second phase of joint projects. So that we have to differentiate or to distinguish the broad initiative Material Digital with long-term goals, basically a representation of materials in a digital way for the whole life cycle. And in the core of this initiative, we have the platform that is just a base to attack all those initiatives and the different kind of materials, different kind of concepts in a simple way or in a connected way in order to make it interoperable. I mentioned that we have in this first phase those projects that was a call of the ministry, and there was a huge response. Almost 170 proposals were submitted, and from those, 13 are being funded. And things go so far from Glass Digital, where the colleagues have an automatic way of casting glasses with different compositions and to make the analysis of high throughput analysis of those glasses and implementing that in a description and a systematic description from the production to the characterization of glass materials. We also have another project on concrete, describing the whole life cycle of a concrete type, based on an ontology, or Joanna mentioned in her presentation, Stahl Digital, Steel Digital, where they prepare or they are working, as she mentioned, for sheet metal production from the casting to the rolling until the crash safety of those components. And among them, there are other different aspects with copper alloys, aluminum alloys, or elastomers, or materials for batteries, and so on and so on. So, and that's the aspect that's broad, covering a very broad area, or a very broad portfolio of different materials and different concepts. And what we're trying to do in the platform is just trying to connect all of them and to bring to a common language. In the beginning of next year, there will be another group of about 10 projects that will join, then increasing even this portfolio here. Well, to start with, and first steps, first things first, we are concentrated, that mentioned John also in her presentation, on tensile tests. It's a very common thing. We're talking mostly about structural materials, and we have to have parameters which describe mechanical behavior in this very different applications. And the tensile test, or the tensile test, is a very difficult or a disseminated type of testing. All the engineers understand what is that, and that's suitable for this kind of description, where to find a common language. I think you are acquainted to the kind of test that we're doing. I go through that, I'm sorry. And very important here is that what we are doing is compatible to the standards. There is a standard for a tensile test. It's about 70 years old, and it's very, very well defined. And we have a very good contact also to the technical committee at DIN, which is developing or taking care of this standard. I followed the discussion this morning, earlier today, and there was also the aspect to where standards do we need so many standards? Well, it did not take about so many standards, but I can assure that we need surely something like a standard for a tensile test in order to define exactly what suppliers and customers of steel, say, or aluminum alloy, just to speak the same language and to define things and not to have any problem in any word. So that, to my feeling, standards are absolutely necessary, and our developments in the platform are conform to those standards. For instance, here, for the tensile test, and we are concentrated as this method of test for metallic materials at room temperature. And we went through with our colleagues from the technical committee. They built a working group on that, and we worked intensively and went through its 96 pages of the ISO norm, which you see the number here, went through those 96 pages and picked up all the different concepts, all the different terms that are being used there. There is a very, it's a very systematic way to build on a standard, but it's not digitally compatible, so that it's not machine readable. What went is to go there and to classify those aspects into primary data, secondary data, and metadata. The definitions are being given here, and I go through slowly those three aspects. First, for the primary data, that what we have during the tensile test, or in advance to the tensile test, or during the tensile test, the data that are generated by the machine or measured by hand from the operator. That means that was we usually call raw data. We prefer to use this name here, primary data. Those are measured directly, and they are deposited in such a way that is a depository for those primary data. Of course, the engineers or the projects, they need some parameters which show how the materials behave. In the examples I have shown before, a bridge or a crane, they work in the elastic region, and we do not want them to go into the plastic region, because that will be actually a failure of the component. So that it's very important for the engineer, for project engineer, to know where is the transition from the elastic to the plastic region, and for that he has a parameter that is defined in the standards to measure. And for us, materials engineers, it's important to give to the project engineer a very reliable value of that yield strength in order to know when does it go from the elastic to the plastic region. And those are the secondary data. That means those data, those parameters that are derived from the primary data in a given way. And those are defined also in the standard, and we separate that, and those are here in this slide, these parameters that are defined. You see for each of those entries, we have, of course, very different. For the sake of simplicity, I concentrated them just to the boxes, but to each of them there are different levels of definitions, which are all content of the standard. And the next step are the metadata. And what we see here is that are all the information that go around from the laboratory, which kind of laboratory and how it's organized and how it's directed, and which kind of quality management they have. For the test piece, from which material it's that, so that, for instance, how to identify it, from which semi-finished product it was machined off, and how it was machined off, so that there are many different information that are to be here about the process, and very important too, about the measuring systems. What about the testing systems? Which kind of it, which kind of grip, which kind of extensometer, or kind of load cell, where they calibrated, when were they calibrated, and so and so and so. That means that the metadata are very important for the quality of the data. And that is for the reliability of a measurement, and that's also the price of that data, primary and secondary data. It's very important to have that, so that all of them, primary, secondary, and metadata, are important and have to be defined very well in order to process it. As a part of our project, my colleagues at BAM they took a piece of a plate of East 355. That's a very common steel that's used for structural applications. And they took out very different specimens or test pieces with different orientation to the rolling direction, for impact test, for metallography, for hardness, and so and so and so. And all this data that are related to one single piece of steel or plate of steel are available for free at internet, so that you can use that. And the idea is that we generated, or we deposited here, the primary, the secondary, and the metadata, all related to this one, so that you can freely use it for any consideration in this aspect. And we use that in our project now. Well, the first step we mentioned before is, of course, the semantic interoperability of that. And we are that's the very usual you would note that that's to standardize and to make it conform for that. And we are working out a core ontology for the platform in order to communicate with those 13 different projects. That means those domains, as I mentioned before, steels, aluminum, concrete, rubber, thermoelectric materials, each of them with a language, each of them with a background, each of them with a concept. And what we're trying to do is to promote a core ontology, which is communicating with upper level or ontologies and consistent with other domain ontologies that are being used by the colleagues. There are different aspects that are being used, and try to promote this kind of interaction. And the development of this ontology, we try to identify the different test methods, as, for instance, exemplary for now for the tensile test, but for the different ones, how to manufacture the materials, how to transform them, and how to produce. It's all those aspects flow into the process and have to be considered in the development of each domain-specific ontology. Just schematically, that means our core ontology has to be compatible to all those from the different projects. Later on, for the huge community, for the whole community. So that what we're trying to do is to have an interface which allow us to communicate between our platform and any different depository which is connected to the platform later on. This is all the aspects. If you see on the back, that's just for an example for a steel plant, and to go in both aspects to define a terminology, to define a dictionary, a thesaurus, and from that on to define broad concepts and specific one. For instance, a yield strength for a metallic material is a different concept for the yield strength for the people of concrete, so that we have to identify those particularities of the domain and to bring both into the ontology and to formalize at the end an ontology where using all to describe it and to have then the description of the core ontology. Work in progress. We'll not go into more detail here, just go to the next step. Well, that's of course how the core ontology will connect it to the other products or to other different concepts that are available away. And just to show how to use now those processes, first, if you go from the primary data that were generated here before, and in order to use that for any kind of analysis or simulation, we have to transform those data to unify them and to make them structure. This is a complex process from the data generation, and we have to bring that in a machine readable aspects. We are JSON, the native JSON, then we try to make them comprehensible for the whole universe, and that's what we need from the canonicalization to put them understandable, to make every node once we mean force, we means everyone will understand what force is being meant. Then to map them, and for that we need the ontology, and to store them in a triple store, and to use that for any process for simulation, for analysis, or even to publish those data. This is what we're doing in the platform. And just to give you an example, this is from our project that is working on concrete, and that's the same scheme, the same idea that they use, and the picture of their presentation and how to derive from the primary data to the output of them and to process them into a given workflow. And that will be the next step, just to talk shortly about the workflows. That means it's at the end, what we use here in the downstream. And if you just consider a simulation process from the user perspective, you define a model, you define a project, you go into the simulation, and the results that are being, you have validated them, and they are given back to the user. What we need is on the back those ontologies describing this part of the process, and the platform would connect all those steps back and forth, how data are generated from each step to the next in a comprehensible form and in a reproducible form. That's then the end vision of our platform to work off. And for instance, for the tensile test, where you go and to define the Young modulus, and to make the same thing and to define that, and to have, for instance, using PyIon, that's the platform that is being used here, taking the core ontology and bring it to the output so that you can describe this kind of workflow for the yield point of the Young modulus of those plates based on the free available depository of ETH355. Those workflows are defined in one of the projects from the 13 projects that we are working with now, or for any other one. And from those projects, a given application or a given workflow that's being defined for a given problem, it has to be validated. It can be, of course, in a closed loop, it can be improved. And when it's satisfied, it goes to the application. And this workflow that was defined, validated, and it's characterized, it can be put into a library and can be reused for other applications. That's, of course, that's one connection, as Joanna showed, to the marketplace, when you can just put it outside, and we can connect them also using the platform that we are developing. Very important is how to bring the whole community to contact the platform, and we have at the moment 4 different levels, how to put them, and different mechanisms, channels of information, how to communicate. For instance, for the discussion of those ontologies in those 13 projects, we have a kind of playground where people come every week and just exchange their results, what they are developing, how they are solving those problems, and interact in order to improve their own development. And for that, also from other ones. And that was just in a very, very short overview what we're doing, and I will be glad to answer any questions. Thank you.
Thank you very much, Pedro. Thank you. So open contribution, open for questions. I'll also check the online. Oh, this was just from an earlier comment by Emanuele that there is a workflow task group starting in EMC to define what workflows are, materials and modeling, workflows, manufacturing, and so on. So
I took note of that. I will give it to our colleagues of the workflows too.
A question I had about the data. So I think in some projects, I know from Joanna, the data are in themselves are also then captured in the RDF triple store.
In the stream, in the work, everything was captured in the triple store.
Yeah, in the Urwerk, that's everything captured. Is that the general approach here in the material digital, or is it basically also that you then have mapping to the data sources, whether they are spreadsheets or whatever they are? So, or do you follow a particular kind of policy on how do you capture the data, connect to the data, and so on in the initiative? Pedro.
It was. Do you mean how to provide the data? Go back to this.
Yeah, that's right. I mean, how from the different projects, how they provide the data to the system, whether they are actually integrated into the system, like that was in the Urwerk project. In fact, even as RDFS, capture of the data instances, or there's different ways of doing it. Or do
you mean the format or the data itself? The data itself, they remain with the data itself, they remain with the proprietary. That means a question that is a very important thing that the IP questions are considered. That means who generates the data is the owner and remains on that. And what he makes available are only the metadata. That means he shows he has results on that material with this and this and this features. But how to contact then it will be between user and owner in a given way. Interesting, and that's because we have done that with, this here is exactly in order to have a repository that's absolutely free. We generated that and make it open at the internet so that anyone can use for that and use for examples. This kind of data is very, very rare. Most of them, even for the public institutes, they have kind of cooperation agreement that are not free for use. It depends on some, they have to be set free by a partner so that it's not usual to have this kind of free data. That was because we generated them.
And how do you see the role here of the top level? Okay, we had that earlier a little bit of discussion, but still, at what level do you achieve this harmonization, right? Because obviously, I gather that your preferred choices here that use BFO as top level ontology. At the same time, you also have then what you call the PMD core, which is provides, I guess, an interoperability kind of layer. Then you have your systems via the metadata and how they're shared. So in a way, interoperability and harmonization works on different levels, right?
Yes.
How do you see that landscape, and what do you see is most important at this stage?
That was perhaps what you can show here, because give an example of tensile test that we are working since a long time, and even for the tensile test, it's not quite easy to promote that. And what we're trying to do is to give it a path, and how are the stones that you have to avoid in order not to fail on that question, and for a given specific domain, which steps or which how the process has to be carried in order to make it available for a large community. And then to put in discussion, because even when we grow, we decided to discuss that in a small group. And when we increase this group and show those results to a larger community, for instance, we go to our annual conference on materials testing and show those results, the next larger group will have any other comments or remarks, because you have to convince people that we need this common language, so that it's a very slow process to integrate that. And a huge advantage is to start with the given standard, in this case of ISO, and to use all those background, because the standards are being discussed since thousands of years. So that if you use that basis in order to improve that and making now those new considerations for the digitalization, then we have a very we can profit out of that.
Yeah. So, if I understand you correctly, a lot of the harmonization really has to be between experts working on a common understanding of the concepts themselves.
That's it.
Without that, you, as we say, you are dead in the water. you're lost. Anyway,
and they have to be open-minded in order to see the wordings becoming digital.
Okay. Yeah. You mentioned the vocabulary. I think you have some tools developed also for people to work together on these shared vocabularies or something like that. Is that
yes, that was my last slide with those 4 levels to put people together, and we have to try to homogenize. Just considering those 13 projects.
Okay.
They are not only very
not available. This is within your community, or is there already something?
Oh no, it's open. It's open.
That?
If you go into our website, there are several levels which are already open, and the idea is, well, the 13 projects is just our first, how could I say, sparring partners in order to learn how to work with so different communities on the one side, and so different levels of integration. In some of those projects, there are many people who are very keen of ontologies, and they are very, very well defined. Other projects are not so far, so that we have to try to homogenize not only different communities, but also different levels of knowledge.
Yeah.
And for that, we're trying to put those repositories and to give help to people to find material and to work themselves to improve them in order to develop this kind of material of systems. Yeah.
Thank you very much. Any more questions here? And if that's not the case, then thank you very much again for your presentation, which now I think means that we are in good time to move over to the panel discussion. But please do stay. We have some people also who couldn't make it. So it's really, Dirk is not here, and I think Thomas, Hanke, and Alexandru also.
Yeah, Dirk is ill. He sent a message some minutes ago that he's not.
Unfortunately, yes. Sorry to hear that. And so it's really, and then Heiner cannot make it due to another conflicting business meeting.
There is really, I wasn't sure.
So we just have basically the speakers.
The speakers and yeah, you can.
So it's the topic is basically up for open discussion. Also with the people online. So people that are, of course, if you would like to ask a question or come to the stage, please let us know. So some of the, I mean, questions I put here for the panel, but now it's just for anyone, for anyone, is what are the current limitations to and barriers to reuse of existing ontologies? So it's more like a questionnaire type of thing. Is it, I mean, one is that there's sometimes, limited access. So that was also mentioned by with this industry portal, or that now there's portals like Math portal as well. So not enough fairness or ontology libraries. There is also a lack of documentation, so that you really don't know. I mean, is that useful for me, or elucidation, conceptualization? And in fact, probably also in our field, I mean, the fact is there aren't really that many ontologies. I think also Heidi mentioned that today. Yeah? So there's a limitation for reuse because there is not much to reuse. Yeah. Any views or comments on any of the above?
Here we see some ontologies that are dedicated to specific point of view, for example, tensile strength measurement. But in the real world, you will not only have tensile strength measurement, but plenty of measurement. And there can be, this is in one area, but in another area, you will have another one. So it means that it can be, the ontology can be either very flat, it means you have plenty of measurement, or you need to organize it in more, with some hierarchy, so that you can access more easily to your knowledge, or you can select it. Do you have, does someone has a point of view if the ontology should be flat here or more deeper? I don't know if this is the right word.
I think it depends on the domain. If you're in a highly specific domain, I mean, you require a high hierarchy, but if you have to model something very simple or specific, I think it's good, or a good choice. Just have a few classes and not that many.
Yes.
That many hierarchy.
But you explain that we want interoperability and so on. And if we want that as a company, but an organization, you will need to have quite a wide view. So you can't have only one ontology in one domain, which is just for one application.
Start by not going too deep. But one of the things which came out of the other session on industrial things is that both Ontocommons, ISO, and IOF are concentrating on a core, which is a few tens of items. And really, that's the first milestone. And I do wonder, I've been looking at the macro, great. And it has an entity called test, which is a subclass of process. And then we got the thing is that under test, do we have 6892 part 1, 6892 part 3, 2, 3 as all distinct subclasses, or do we do test, tensile test, and then, but then do we do test, steel, metallic test, polymer test? Well, actually, we can't say you just do both, and they can be. It's not a problem. The fact that 6892 part 1 is a tensile test and a metals test is something which can be in the ontology. So when you search for what test data do you have, you can filter more whether it's tensile test as opposed to a fatigue test, whether it's materials as metals as opposed to polymers. It seems, but then we might go down into what sort of properties that produces. And but having them, yeah, I don't know. But getting this core thing that there is such a thing as a test is probably the first stage. There's a test and a test specimen, and the test specimen preparation and conditioning process as top level things, and then let the subclasses of those just evolve as people see need, as you need.
Yes, I mean that's what we're aiming to do. Of course, I mean we presented a bit on that yesterday, you know, on this Cameo, and but there's still so many different. I think it's also getting the right people and the right communities together to do that. Is part of that. Which has there isn't the community that's focused on saying, okay, we need this. It's almost like the middle layer, right? It's not a domain. Well, whatever you.
I know it is a worry that people basically want to have their domain in the title. What they're doing tends to be more generic. And I know you talked about the workflow, and I'm involved in this simulation data management metadata thing, which is mostly about workflow for simulation. How exactly does it differ from workflow for doing a test? Not really very much at all.
It's in silico.
Yes. Hope you can hear at least some of that online. I know it's difficult. Yeah, I mean, that was also the other question I had was kind of already that we know the best practice for developing a harmonized approach, you know. So in what communities, so like the IOF, the Onto Commons, and you know, should the approach be top down or bottom up? Because I guess from what you're saying, you have to have a certain amount of top-downness about it. Otherwise, you end up with that situation that the simulation people, the characterization people, will define the workflow they like, and then you know.
Yeah, it's a question of whether the technical committee producing the specific test standards can assign a URI to a UTS value produced by their test standard, because that's a particular type of property, which is what you're going to use for material selection or whatever. It will be a value, this sort of property as produced by this standard, and if you've got a range of materials, you can then compare it directly. But it's a question of identifying that particular property, and whose job is it? Well, really, it's their job.
Yeah, that's a community, yeah, specific.
But they don't know that they need to do it. Nowhere in ISO or BIPM is anybody assigned a URI to the meter. A bit of a problem, really.
So nobody
has assigned the URI to the meter.
Yeah.
QUDT has assigned the URI to the meter, but who are they? They're just these people. It should be ISO or BIPM, but they don't know they need to.
Yes.
Yes.
Yeah. Well, yeah.
Also, they'll make it difficult. Change the URI when they change the definition of the meter.
Yeah, it was like the other question was from the projects. You know, there are so many different I mean, I think they're all about the same thing. So many times there are common generic concepts, right? Workflow, property. So why can't we reach an agreement on those at least?
What is the property? Yeah. Different word. First of all, people think in terms of owl. No, we don't mean owl.
No, materials.
So we have to prefix
materials property. Or product.
I think that this has to do with the nature of humans, because it's often said that there are many opinions as people, so
Yes.
Everybody will see stuff differently.
From there.
It's the same, but everybody sees from a different perspective. So that's one of the main problems about modern ontology. Everybody sees reality from their point of view, and it's different. But it's valid because
Yeah. Yes, of course. I mean, one can also, one can look at it the other way around and say it only lays bare, it only shows the differences that already exist, right? I mean, it's not that by not using ontologies this problem goes away. It just makes it clear that there is a problem.
Yeah. Well, that's right. All the time people are doing it. People understand the context. As soon as you get the machine to do it, they don't. So we have to put in an extra layer.
Yes.
Maybe I have a question or a remark.
Yeah, please.
In ontology, we try to define as precisely as possible everything. And in the life, we know also that things are not exactly as expected. Uncertainty, not exact things, so on. Is there a part in material aspect where we deal with such things? So that we, for example, we cannot do exactly the same thing. There are some dispersion of property, unexpected results, things that are not explained yet, and so on. Or do we have the ability to clarify this knowledge to discover?
That should be exactly why it's a very good and very important requirement for an ontology in my view, that it should be able to do that, not to. I mean, it's in a way the difference between, I would say, between an ontology and a data system. The role of the ontology is to give more context, and what you're saying is type of context. Of course, you have to determine what is the context that is important to me, but in principle, it's a description of all sorts of things, including all of these uncertainties, and that things could vary and so on. But in the practical level, there's always, I mean, there will be a decision to be made, right, of how you practically capture that. Otherwise, the whole system blows up just because you want to, all sorts of things and so on. But yeah.
I mean, I do standards, but I've been in the industry data standards and material standards. Are the materials committees in ISO interested in this at all? What do they regard as not their problem?
I
don't know. I mean, I know that the sort of in terms
I'm not involved in the committee.
Engineering, in terms of engineering, I know that the process that the committee is to do with process plants and that, in terms of designed the pressure vessels do have liaison with PC1, A4, SC4. They've agreed. We do the designs, maybe the terminologies. We don't do anything to do with data models or ontologies. It's your problem, and there is a liaison to deal with issues. I've never come across anything comparable in the materials field. So going forward with materials ontologies, it might be necessary to create something like that, so that the people who are designing the test standards. I've got a feeling that the 6892 Part 1 actually has a data format, doesn't it, in terms of recording the strain curve, I think. But it's a comma separated file. So they've done a bit, but then going further, they would want to hand it over to somebody else.
Yes, absolutely. Yeah. I mean, from what I know from, let's say, Jim Austin from, like, who's at JRC reference materials reference. They interested, involved in the machine readability side of things. So that's to some extent the first step. It will tremendously help to use or reuse the standards in. At the same time, I think Pedro is maybe still online. I mean, this work of actually going through each, the whole standard and all of the, the procedure, and really mapping that into an ontology representation is a completely different level. But it was great to see that you're really working with people.
That was very valuable, yes. And the first, my first draft of this data structure, well, it's similar to that was at the end, but it took a long time, and the people are very careful and put each word into the balance and to define. And at the end, we got a result that was really compatible. So that my first draft, there are many things that were not consistent. And then this consistency can only be reached with a very careful discussion in this specific aspect. And that was the value of doing this exercise for tensile test. And it has to be done to each one by step.
Yeah. I mean, it's great, but do you know of any other examples of that having ever been done?
Not. We are working on the hardness test too. And there is a perspective which Rana mentioned, also the fatigue test, and fatigue is a very, very broad aspect. And there are some groups working in IMM. We are working with normal fatigue test. At BAM, there is another group working on the LCF, a little cycle fatigue, that's similar but has also its specificities, so that we are more and more spreading. My dream would be now to extend also for non-destructive testing. Unfortunately, we could not that. There was one colleague was doing that for thermography, but it will not be possible. We have to find another way, and then to the analytical science, and then would have for destructive testing, non-destructive testing, and analytical science. That will be a very sound basis in order to show how to proceed. Then each community has to work on.
And how is it seen at the standards organization itself to do this work and to be involved in that, and also, is there anything that could then become almost like a part of the standard in future versions, like this type of implementation?
Okay, that's my personal view. Okay, I'm not talking about PAM or IMM, but if you go to the president of DIN, every third word he uses digitalization, and he knows that it has to go in that direction. But as soon as you go from the 7th level of DIN down to the technical committees, very soon it spreads away and no one talks about that. so that what I tell to my colleagues at the Untitled Test is that we are doing pioneering work, because this is it's a germ for this kind of work and to improve, so that what they're doing now, and if in the first level they were helping us to improve our ontology, and now they notice that will be necessary, so that we are just collecting material. When there is a new issue of the standards, then they will present something in that direction. That's what we are working. Every 4 weeks we have a meeting, and we're preparing this material very carefully, but to do that. And what I do expect is that it will be common for all of them very soon.
Thank you. It's very. I know that the issues, but also promising at the same time. Yeah. And then finally was the question of how this harmonization between material science and other domains. Okay, we did touch a little bit on that. Is going to work. I mean, you had that also in your questionnaire. I think, well, it was from your questionnaire. Should this be taken into account straight away? Do we need first to get the material science field in order? Yeah. What's your view? You put it in there.
Yeah. So actually, in the project, we tried to already capture the manufacturing and also the data about the experiments. And we did this representation of manufacturing plus in that case, the fatigue test and properties of materials using the common framework of MO. So all the concepts that you describe manufacturing and also the material, the characterization process, that are aligned to a top ontology, which is HEMO. And HEMO provides all the framework that enable us to describe the sequence of processes, how do you say, the changes in the material after each process. So then the material will have different states during the process. So the framework they use is all harmonized based on the top level ontology. And I think potentially this is a way to go, to have a top level ontology that provides the framework that can facilitate the alignment between the domains. Potentially, yes. This is what we did for this project. We consider the same core ontology. Yeah.
Now, I have to ask, but you don't have to answer. Within the Fraunhofer type of projects, there's BFO and there's MO projects, right? Quite a lot of them on each side. So why and where is this going?
I think there are, maybe Pedro can comment better on this, but I know that in PMD there are actually efforts in working on the alignment, right, of these different frameworks between MO, BFO. Is that correct, Pedro? This is what I'm a little bit aware of.
Trying to connect that, but I'm not a specialist on that, so that's best go not to give the precise information. Perhaps Hank is his hearing could give a hint on that. He's in the chat.
Let me see. Oh.
Maybe there is a message.
Yeah. I cannot see at the maybe. Yeah. Oh, there somehow. Okay, there was a message about that. That was earlier about testing.
Yes, he put a remark, so you cannot hear me now. He tried to go.
Yeah, hang on. If you I should also be able to do that, but otherwise, if you raise your hand, it's probably easier for me. Then I can maybe add you to the stage. People.
Yes, HB.
HB. Yes. No.
Be able to.
I mean, yeah, maybe we cannot hear you.
I think only
Yeah, this is maybe not. I'm not on the right level of.
Yeah.
Of user here to add people. It seems no.
Just Catalyst attendee and not as a speaker.
Yeah, and I'm also not the right or this me. I mean, this laptop doesn't seem to be at the right level to connect it to.
Comment on which top 5 different top ontologies are these. I think it also depends on how comfortable you are with the knowledge that we have about ontologies.
Yeah. Okay. I mean, yeah. It's maybe some other time we can discuss about that. Yeah. There was also that. I don't think there is like an easy or answer. And people, yeah, exactly. Yeah.
Because maybe some people agree more with some concepts potentially provided in BF4 and in MO, or the knowledge that we have about.
Yeah, it's about
our decisions that we have to undertake.
Absolutely, yes.
But with the work, will it be compatible with UOF? Because material is linked to industry practice, certainly in results, and it's a product. So certainly in UOF there is the handling not only assembly but materials, so there should be something common. Have you have a look at that, or?
So from myself, at the moment, I'm not too much involved in the actions of UOF, but we have colleagues in our institute, and tomorrow, I think it's tomorrow, there will be some sessions on the material science domain as well. So I myself have not looked into it, but the colleagues in the team, they have played some role in the group, in the institute, I'd say, in the form of our IWM, and definitely I cannot comment about if the work that we did in this project if it's compatible or not with IOF, because I'm not fully aware of all the models that exist or that are recommended from the IOF. But I think this would be is a very pertinent comment, and I think it's something that we should definitely aim at. Yes, the goal is to also get us closer to industry, right, and to also actually use the standards in industry.
Yes, yeah. I mean, IOF is trying to develop this system of ontologies, but of course, that, as far as I know, it's all BFO based on ecosystem. Not even Dolce, I think, or not so much anymore. Not hard. So yeah, I mean, it's an initiative, but you know, at the same time, that's their decision at the moment. And obviously, we are aiming now with the Onto Commons to do this type of integration as much as possible. Where this is all going to go in the future, yeah, there's many discussions to be had, yeah, especially due to the developments now also with MO and so on.
I think maybe the fact that we use ontology system in line with some comment that was yesterday in one of the talks, that potentially in the end what we will have is ecosystems of ontologies, or systems of ontologies and potentially have some systems that are more aligned with BF4M. Ideally, we'll be able to harmonize them and do this
Yeah,
goal as well
exactly.
from Onto Commons. But,
I mean, they're all, hopefully more than one will be standardized as parts of ISO IEC 21838. BFO is 21838 part 2. And I think there's steps to get, not going terribly quickly, because it's not obvious what the industry benefit is, they're going to get funding, but to take some of the others, the other parts of ISO 21838.
Yes.
And the important, the useful part of 21838 is 21838 part 1, which says what a top-level ontology is and what it has to cover. And so that's extremely useful. I mean, it has to cover how situations change with time, how possible things are dealt with alongside real things. It makes sure that any top-level ontology, which is standardized under 21838, will have comparable sections, and you'll be able to compare one with another, so, which is useful.
Okay, thank you very much. I think, yeah, we're pretty much.
Yeah. The copy is ready also. So.
Thank you again, everyone online. Thank you, Pedro, for the great presentation. Much appreciated, and the discussion. So, and from my point, hopefully to see you in Darmstadt. Yes.
In 2 weeks' time, we'll be in Darmstadt.
Yeah. Oh, good. Hope everything goes well. Thank you.
Okay. Bye-bye.
bye.
Bye.